So I'm very pleased to be able to introduce Professor Meng Chang from the Electrical Engineering Department at Princeton. Meng received his bachelor's, master's, and PhD degrees from Stanford, and despite the fact that he got his PhD as late as 2003, he's already won numerous awards, not only the NSF Career Award and the ONR Young Investigator Award, but Howard Wentz Junior Faculty Award and from Princeton, and also the Engineering School Teaching Commendation, Terman Award from Stanford, Hertz Foundation Fellowship, Stanford Graduate Fellowship, the TR35 Award, and others that I need not go through the entire list here. But he's well known for his work in optimization and networking, and he's going to share with us some of his perspectives on that today. Thanks.
Thanks, Phil. My pleasure to be here. Thanks for sparing me the embarrassment of going through a laundry list of boring things. Indeed, this is a talk about perspectives. I decided to give a talk here and several other places on something that it's hard just to say it in one paper. And I find these kind of venues the best places to describe those viewpoints. And the viewpoint today is what I call beyond optimality. If you think about optimization, that word applied to networking, people think, well, the standard answer is I'm going to use it to compute some local global optimal. But it turns out that there's a lot more that you can do with optimization for communication networks. So we're going to see today things ranging from modeling to quantifying architectures to build robustness against the stochastic dynamics, even as a feedback mechanism, not inside the network, but in human engineering procedures. And finally, also complexity performance trade-offs. So in a lot of these applications, you don't see computation to the exact optimal being the holy grail of the subject. Instead, you're going to do something more like using optimization as a language, just like English or C, and use that language to describe, to talk about how you think about network engineering. You've seen a lot of these papers, and a lot of these papers are becoming more and more boring today because they end up proving things like this, due to composition, utility maximization, some asymptotic convergence, subject to step size tuning, and so on. And let's try to move beyond these and move to more challenging and fun stuff. This talk is itself an optimization problem where I try to minimize the amount of things that you can just get from downloading a paper, subject to the constraint of being somewhat self-contained, and the variable is the content at the time. So unfortunately, I got to do the optimization. You're going to suffer through the outcome of that optimization. I'd like to acknowledge many wonderful collaborators within academia and industry. So let's set the stage first, using optimization as a language to talk about resource allocations. So anytime you've got a constrained decision-making problem, think of that as an optimization. It's a data structure with 4 fields. One is variable, design freedom you have, and constants are those that you cannot vary. You have got some goals and some constraints. So anytime you've got these 4 data structure, you're talking about an optimization problem. This sounds quite abstract in general, and we're going to illustrate in this talk 3 successful technology transfer into commercial systems through our industry collaborators on things stretching from broadband access to internet backbone design. So what kind of objective functions are we talking about? Usually 2 types, cost and utility. And they don't have to be additive, but let's say they are. Okay? So this cost can depend on all kinds of freedom, like sum of the power. And utility, this is a funny thing. Okay? It's coming from economics literature, usually assumed to be increasing, concave, and smooth, but they don't have to be. Okay? Although increasings usually are pretty much true in all cases, don't have to be concave or smooth, but if they are, the math becomes much more tractable. Usually think of that as a function of throughput, doesn't have to be. It could be a function of delay, energy, and so on. Now, utility can be used to model a variety of things, ranging from efficiency, to traffic elasticity, for example, more concave, more elastic. User satisfaction, like MOS scores for voice and video, based on user perception experiments, and even fairness. So those of you who don't know, this is kind of an interesting thing, that you can quantify the notion of fairness among competing users in a resource allocation vector X that is feasible by the definition so-called alpha fairness in economics literature. So say that X is alpha fair as a vector. If for any other feasible vector Y, this summation, the deviation normalized over X to the power alpha, is negative. So when alpha is 0, that's a very unfair allocation, actually can lead to starvation. Alpha being 1 is the famous case of proportional fair, and alpha goes to infinity. This tends to becoming a maximum fair allocation. So far, that's the definition. It turns out that if you maximize a certain parameterized utility function, then the resulting optimizer will satisfy this definition, and therefore people call those utility functions alpha fair functions. They're of this shape when alpha is not 0, and log when alpha is 0. So this is by now very famous thanks to especially Frank Kelly's 97-98 paper on proportional fair allocation. So it turns out that there's a belief that a bigger alpha means more fair, and that is true if you compare alpha 1 to infinity, but anywhere in between, actually I haven't seen a paper saying why alpha 3.5 is more fair than alpha 3.1. So there needs to be some more asymmetric study on certain widely agreeable notion of fairness becoming a monotonic function of this parameter alpha. I haven't seen that. And also, I haven't seen a rigorous study on the effect on suboptimal solutions on your fairness gap. You can well define optimality gap, but what would it mean to say there's a fairness gap? And that connection is still missing. But nonetheless, you've seen utility being used to model efficiency of allocation and fairness and so on. But there are other things beyond performance in a standard way. For example, availability of service under attack, various aspects of security, and various fuzzy concepts that are as important as performance, like throughput delay. Can utility be used for those? It's still ongoing work by many various groups. Well, leaving constraints, leaving objectives for a moment, coming to constraints. There are usually 3 types of constraints we face. One is inelastic individual QS constraints, just hard constraints in a user need. 2 is technological regulatory constraints, ranging from the simple ones such as maximum power to much more interesting ones like net neutrality constraint. 3 is feasibility, and this is the tricky part. If you're coming from an information theory background, then it could be capacity region, if you know that region. Queuing theory background could be the stability of the queues, the region for that. Or it could be the achievability region under particular physical phenomena and the particular physical layer constructs. For example, 3 typical phenomena in the network: congestion, collision, and interference. And they are typically represented by additive, Boolean, and multiplicative constraints. They have different degrees of freedom, and in some cases, there's pioneering work in the industry that defined a whole sector of industry, followed by analysis or inspiration of seminal work like Kelly's 98 paper analyzing congestion control, Tassiulis Efremidis' 92 paper analyzing constrained queuing networks, maximum weight matching for throughput optimality, or Foschini's work extending Qualcomm's near-far problem solution for power control. In all 3 cases, there's some very prototypical optimization problem being involved here, whether that's linearly constrained utility maximization, convex constraint, this is a weighted rate maximization, or SIR constrained power minimization. Okay. So these 3 classical problems have been studied by thousands of papers over the years. And interestingly enough, they all use feedback in the network, either implicit or explicit feedbacks. So you can start by modeling using optimization as a language if you specify objective constraints and freedom and constants. Or you can start from the other direction. Say that, give me a given protocol, and I'm going to try to reverse engineer the underlying problem being solved by this protocol. Sometimes it's an optimization by the social welfare system. Sometimes it's an individual selfish optimization interacting as a game. So this is the mentality of reverse engineering. In contrast to optimization of the network, this is optimization by the network. The elements in the network act together as a distributed optimization machine. You may wonder, well, if I already have the solution, why do I care about knowing the problem? Well, that's because often these solutions came from ad hoc engineering, intuition-based hacking, and they certainly have done a lot of impact, and sometimes it works very well, sometimes it doesn't. So how can we understand them in a systematic way? How can we design future ones in a rigorous foundation? And that's where forward engineering can follow reverse engineering. Here's a quick summary of our current understanding as a field of reverse engineering. Well, you don't see physical layer here because thanks to Shannon, people pretty much know what they're talking about from day one, if day one is 1948, okay? Capacity and rate distortion limits. But upper layers tend to be designed based more on engineering intuitions. However, most of them have been reverse engineered over the last 5 to 10 years and shown to be implicitly solving an underlying problem. That is, you can view the trajectory of this given protocol as the trajectory of a certain algorithmic steps towards solving an underlying problem, such as the basic narrow utility maximization, such as so-called stable path problem for inter-autonomous system routing, and some game-theoretic reverse engineering for contention resolution systems like those in 802.11. So I'm skipping a couple of the slides because I'm trying to make sure I don't overrun by too much. So part one, just want to lay the foundation and show you some of the modeling typical frameworks and languages. And now I want to say something that's a little bit more on ideas, driven by the quest to understand architecture. Now, architecture is a big word, a fuzzy one. By that, we mean more specifically here functionality allocation. That is, who should be doing what and how to connect them at what time scale. For example, how would you contain error, contain and correct error? You can do that at the physical layer with forward error correction codes. You can do that with ARQ, hop-by-hop feedback. You can do that with multipath routing. You can do that at the end-to-end level with CRC check. You can do that at network coding, at the application level. So it's not clear exactly if that there are 5 people capable of doing the same job. How would you allocate the job, divide it, and let each person do part of it? Or how to resolve the bottleneck in terms of resources in the network. You can do congestion control, let everybody back off with their transmission source rate. You can do alternative routing. Don't use this congested path. Use a different path. You can build a fatter pipe, say by power control, maybe at the expense of hurting some other links in the network. Or you can just be doing local neighborhood contention resolution so that they don't contend too frequently. Again, who should be doing what at what time scale, how to glue them back together. Another way to ask the question is, if you're AT&T and Microsoft and Cisco and Qualcomm all come to you, I thought this would be a private, just casual conversation. It turns out I have to sign some release. I didn't even read what I was signing. So probably I should be very careful talking about things now. But say, you're an operator and some big companies with different specialization of their domain come to you and say, you know what, your problem I can solve for you. You don't need to pay others. Maybe you can pay for connectivities and just the physical layer, but don't pay any premium for their value added because I add all the value that you need, right? In fact, this does happen a lot in the industry. So the question is, in some sense, they're all correct. A lot of problems, you can solve it at this layer or at that layer, by this functional module or by that functional module. The question is, what is the most cost-effective, evolvable, stable, robust way to do that division? In other words, which stock to buy here, for example, Microsoft says Qualcomm. Maybe the right answer is, in today's market, don't buy any, but I guess the better answer is to buy Microsoft stock for very obvious reasons. So you think of, in general, there are many tasks you want to do, and there are many degrees of freedom possibly under your control, and this bipartite graph shows essentially which degree of freedom can impact what task. So now you say, ooh, I want all these tasks to be done, and I have some subset of these degrees of freedom traditionally residing in different so-called layers. Now, how should I find a matching in this conceptual bipartite graph? Now, if you think about architectural questions, it's been raised everywhere. For example, in our related disciplines, such as information theory, you see this standard picture in page 1 of the textbook. And Shannon showed that for certain models, like point-to-point with no feedback and no complexity concerns, the job of data compression and job of transmission can be separated without loss of optimality. And that is a very powerful architectural statement. And it means that you can have a digital interface here and here, going from analog to digital, and that would not hurt you in certain models. It might hurt you in other models, but still is an inspirational architectural statement. In control theory, in serial computation theory, you see these pictures in page 1 or 2 of the textbook, and they mean that these people in our related disciplines have thought long and hard about the kind of architectural statement that can be quantified. And they've become part of their blood. It's so natural to them now. Now, what do we have in networking then? This is a standard picture you see, but this is a fuzzy picture because the boundary here is not clear what exactly do they mean. I mean, the boundary means that you don't get to see and you don't get to control everything. You rely on the service provided to you from the layer below. You provide the service to the layer above you. But what exactly is this boundary? Right? And what's the best way to do the division? It's not clear always. You can do things end-to-end. You can do things within a network. Sometimes you can just let end hosts be very intelligent. Sometimes you help with shaping and policing on the edge. Sometimes you start dropping packets here. Sometimes you let intelligence reside within the network. This is the wireline internet. In the wireless ad hoc networks, even more intriguing questions. And between control plane and data plane, control plane making measurements and probing the data plane, and then does some computation, put the control signal back to data plane. What job should reside in data plane, what in control plane? In all these cases, it's not exactly clear. How do we design this job division? How do we divide up the job in the functionality allocation? So something that a lot of people have been working on is called layering as optimization decomposition. Try to understand layering not as an ad hoc engineering artifact, but as something that pops out of a top-down principle-based design flow. Decomposition of an optimization model. It's not the exact value of the optimum solution that we really care about that much. Is the decomposition that matters most, because that gives you the boundary of the functionality allocation. So the flow roughly goes like this, that you start modeling the whole network by a generalized network utility maximization. So the utility doesn't have to be exactly utility as a function of the throughput. It could be, as I just mentioned, a variety of different objective functions. And the constraint sets could be integer valued, non-convex even, with a lot of different degrees of freedom. Given that problem, you want to find decompositions that break it down into smaller problems with a smaller number of variables, observing smaller number of constants, possibly solving for a different objective function than the original gigantic mother problem. And now, for a given decomposition scheme, and there are many of schemes possible, we call that a layering architecture, and the decomposed subproblems corresponds to different layers. The functions of primal or dual variables will be identified as the correct interfaces coordinating the layers in terms of what they can see and what they can do. And this decomposition happens both horizontally, meaning over disparate geographically located network elements, as well as vertically, meaning across the functional hierarchy, such as the 7 or however many layer OSI stack. And then the gluing back together will happen at different time scales, possibly, and using either implicit or explicit message passing. Of course, you hope that the message passing will be simplified down all the way to only implicit message passing on a very infrequent basis. Sometimes you can do that while still hoping for optimality. So there are basically 3 steps in this design flow now, which is very much a first principle top-down approach. You declare what you want and what you can vary. And then you search for a solution architecture based on a particular decomposition. And finally, if time permits, you look for alternative architecture coming from alternative decompositions. So this framework has many, many papers that have different titles, joint this and that, that and this. In fact, if you look at the permutation, right, in the sum of 7 choose I, where I goes from 1 to 7, that's a pretty big number. Then for each such cross layer, you can have like, 5 different meanings of what you are crossing in terms of what you can do and see. For each idea, there are about 5 different groups solving at about the same time independently. For each group, they're going to try to publish somewhere between 3 and 10 papers, say 3. So you add up that number, is a pretty big number, and that's a very disturbing sign. It means you should get out of that field as soon as you can. So what we try to do is to say it's not complicated at all. There are technical challenges, I'm coming to that in a minute, that are true hardcore challenges. But they are also just becoming a template you can start filling in very easily. And underlying the template, there are only 2 very, very simple things, conceptually very simple ideas. One is to view the network as an optimizer, as I just said. The other is to view the process of layering as decomposition. So if you strip down all the complexity and the detail variations, it boils down to something that's conceptually very simple. Now, you wonder, this decomposition thing, how do I do this decomposition? We're not going to go into detail of that. There are many nice survey articles already in print. The standard technique is so-called dual decomposition or Lagrangian relaxation. That's mostly widely used, but there are other choices like primal decomposition, a punitive function that leads to possibly decomposition. And there are different combinations you can do. At different hierarchical level, you can partially do it and later do the rest of the coupling, and then you can pick different time scale choices. And it turns out that there are so many different combinations that we want to construct a user manual. So this is a collaboration with some other folks in Asia and Europe trying to come up with a user manual. And it's not just intellectual curiosity, because it turns out that if you go for different compositions, that can lead to different algorithms, each with different engineering implication as to what the resulting protocol stack would do for you. And more interestingly, you can represent the same given generalized num problem by an alternative representation, which certainly don't change the optimized value, but it does change the structure of the problem. For example, adding redundant constraint. Seemingly innocent, but it may lead to opening the doors of even more decomposition possibilities. So you can parse it from back there, but basically this is a snapshot of this user manual we're constructing. This is the general template where we break down the procedure into 3 parts. First part, you start with engineering descriptions. You end up with one generalized num representation, one problem. Okay. Second block of procedure, you break that one problem by decomposition methods into n smaller problems. Still no solutions, but you've got n problems. Third block of procedure, you find a distributed algorithm to solve. Hopefully, the way you decompose them is inducive to finding a distributed algorithm to solve each of the n subproblems. Okay. So you start from engineering description problem to a particular protocol stack. And this just shows one of the many papers that go through essentially this procedure with a particular path that's highlighted in yellow here. And we're constructing this website, let you know when it's done, and then you can click on many, many papers, and each paper is just one yellow path through this flowchart. So can we automate this? Automate what? First, enumeration of possible decompositions. 2, comparison among the ones you've generated. Turns out this is very tough. Okay? It's good to have a dream like that, keep people going. But this is very tough. First, enumeration. Exhaustively is very, very challenging because alternative representation of the same problem can lead to further decompositions. And some of them would degenerate into equivalent classes. Second, comparing. This is even tougher because compare against what metric? Speed of convergence is one. Robustness against many things. The amount, locality, and symmetry of message passing. Trade-off between message passing and local computation. And even more fuzzier metrics to compare with. A lot of these metrics of interest, we don't have the mathematical machinery to analyze or even to tightly bound them. So it's very hard to even get each individual axis done, let alone do a trade-off analysis to compare among the alternatives. So far it's all just manually done. Okay? You manually enumerate, you manually try to compare, and see if you come up with one alternative architecture that makes most sense for your application. Now, decoupling is actually not just difficult because it's hard to enumerate or compare. Sometimes what you have, this optimization problem, is coupled in such a way that it's just hard to decouple it. I'll give you two very quick examples. Each of these two examples were started with industry collaborators, and we're fortunate to have industry people take on the analysis and then put it into, some cases, products. But I will not go through the details. That will be two separate talks. I'll just highlight one aspect, which is decoupling is not always easy. So this is first case of a DSL spectrum management. You've got some broadband access using a combination of fiber closer to the neighborhood, followed by copper wires. If you live close enough to central office, copper wire directly to you. This could be, say, ADSL, VDSL, that use discrete multi-tone transmissions, kind of OFDM. And one question is, the copper lines are not fully twisted, so they still emit electromagnetic radiation against each other, and at high frequency band, that interference becomes substantial. People in that community call it crosstalk. And your job is to decide what power spectrum density should you shape your transmission so that the crosstalk doesn't hurt you too much. And system-wide, you want to find out for all the users, what is the rate region that can be obtained. So for a given fixed weights W, you want to maximize some of the rates. You can vary the weights, and then you get the whole boundary of the rate region. The rate is the sum of the rate you get on each tone or carrier indexed by K, which, assuming that interference treated as noise, log 1 plus the signal interference ratio. This is the end user signal transmit power at tone K. This is your interfering neighbor M's. And alpha NMK, it is the crosstalk channel gain from user M to user N on channel K or tone K. And this is some additive noise term. And the variable is the PN case. So this problem, it turns out to be a very challenging optimization problem. It's non-convex and is coupled across both users and tones. So these are two different challenges. Convexity is the key towards tractability, towards proving global optimality, whereas coupling is the bottleneck towards distributed solutions. You've got both bottlenecks sitting in front of you. It's been well studied for many years with a revival in 1992 on this so-called dynamic spectrum management problem. So there are many different variants, many acronyms going on here. I'm going to show you a version that's in collaboration with Jianwei Huang, Rafael Sandrilan, and Mark Moonen, called ASB, Autonomous Spectrum Balancing. Of course, when I show a comparison table like this, I always make sure that it highlights the best part of our algorithm. So it's no surprise that this is the best in our viewpoints. It's autonomous, low complexity, and near optimal performance. We do not have theoretical proof on optimality, gap, worst case. But empirically, we run it on very realistic industry-grade simulators with very realistic channel conditions, and it always comes up very near optimal. what is the basic idea here? Ignore all the rest. Okay, I will only spend 1 minute on the idea and move on. The idea is the following. If you know congestion control literature in recent days, you know that there's idea of pricing, okay, congestion signaling. It's a dynamic, real-time changing of information from the network to the sources so as to align the selfish interest into a social welfare maximization. So can we do that here? Not really, because among the users, they cannot easily do message passing. And they cannot easily do it with central office either for traditional reasons. So within the same user, across all these 256 or 4,012 tones, you can do dynamic pricing. But across the users, you can't do that. But if you only allow a selfish maximization, it ends up something called iterative water filling. And that is often quite suboptimal. So the idea in the ASP is to add a virtual line, a reference line, sitting right next to you. And when you do a selfish rate maximization, you try to imagine somebody you need to protect. Okay. So what is the parameter describing this imaginary somebody you're protecting? That is, part of the details here. But it turns out that there are pretty robust ways to do that. So you're going to do a one-time handshake with the central office to get the reference line parameters, and that serves as what we call static pricing. And static pricing would have worked very badly, except this is a DSL case. So the wires, channel conditions, do not time vary too frequently. So for static coupling, it turns out static pricing works out pretty well. Okay? And let me just show you one of the represented plots here. You're looking at 2 out of 14 user trade-off rate region, and this is the best rate region you can get. In red, iterative water filling, totally selfish, give you this. Excuse me. Autonomous spectrum balancing, the one I described, it turns out give you a very close to optimal solution. And if your reference line parameter is way off, you're going to get worse. But we've run many sensitivity analysis. You can see that in the paper as well. It still works remarkably a robust way. So that's one sort of a newer technique being developed, static pricing for static coupling. Here's another different story. Power control, single carrier, but wireless network. Okay, so the channel conditions fluctuate quite fast. Say you look at 2 users. If this is the achievable rate region, again, it doesn't have to be convex. Okay? If it's non-convex, that's another challenge. I'll come back to that towards the end of the talk. For now, let's assume it's convex, but it's coupled. It's coupled in the following way. Your objective is a utility function that depends on the power as well as the signal interference ratio, which is a function of the powers. Your constraint is that the SIR assignments must be feasible. So there are certain dots in the SIR plane that are not feasible. No way you can have a power allocation that can give you that point because of interference. And you can vary both the power and the SR assignment so that you get to the best point on the boundary as defined by the intersection of the predetermined boundary with the, these red dotted curves, which are the contour lines of the utility functions. So how do I get to this point? If you have a centralized solver across monitoring all the cells in the neighborhood and controlling all the base stations, then you can solve a convex optimization here if the utility is concave and get to that point. But the challenge here is that each base station would like to mind its own business, and you cannot easily coordinate across the base stations. So you can allow base station talking to the cell phones, but you can't let all the base stations become centrally coordinated by one guy. Then how can you get on to the boundary and then move to a point defined by the utility function as the best boundary point? Now this problem has been long studied in different special cases. For example, famous special case, if you block the SR assignment from the variables, this is a constant given to you, fixed and assumed to be feasible, then the problem of power control to achieve these SIR target is well studied by, say, for skinny mutagenic. So when you bring them together, it becomes much more challenging. And people thought about how can I extend for skinny mugenic power control. Well, over there, a key insight is that the whole problem can be transformed into a linear algebra problem, where you are essentially computing the right Perrin-Frobenius eigenvector, the right eigenvector corresponding to the Perrin-Frobenius eigenvalue of a matrix describing the topology of the network. But if you want to do a mobile-based local update of these eigenvectors, it becomes very hard. For example, you can try to do decomposition. At least we tried and it didn't work. But it turns out if you do a change of variable, changing the description of this boundary from the algebraic description based on right eigenvector to one based on left eigenvector, it turns out the left eigenvectors do have an ascent direction that is locally computable. So why that happened, I don't know. We just run into that. But it shows that a change of variable can reveal hidden decomposability structures that the original standard representation of the optimization problem may not give you. So let me just skip all these. Those two examples just serve one purpose in this talk, which is decoupling is not always easy, but there are case-by-case hard work that you can put in. I hope that it helps. So I'm leaving behind this architecture story because it's kind of old story by now. Maybe 3 years ago, it's a little bit more fresh, but now it becomes talked about enough that it becomes a little bit less interesting. So instead, let me step back and take a look at what exactly happened in 1998. Among other things, Frank Kelly published this seminal paper on congestion control, understanding distributed rate allocation by economic model, or by this congestion pricing model. Now I compare that with Shannon 50 years before that. Before Shannon, people worked on communications as well, and they tried to design a finite block length code word that protects the signals through the channel. But Shannon says, for one moment, let's turn away our attention from constructive codes, but look at what would happen if we have asymptotically infinitely long codes. Then the law of large number and large deviation theory kicks in, and then Shannon was able to provide both fundamental limits, like capacity, as well as architectural statement, like this source channel separation principle. Of course, later, people have to design finite block length code words and design a practical system. Now, before 98, people have been looking at the coupled queuing dynamics. How do I look at many routers cascaded with each other, and the arrival of the packets are shaped by the previous routers, and how does the queuing system evolve? And that becomes very intractable. But Kelly says, for one moment, assume these were deterministic fluid flowing through the network. Then what would happen? Well, it turns out then optimization and decomposition view kicks in, as well as control theoretic, game theoretic, economic theoretic viewpoints. And now people understand network protocols not as ad hoc designs, but as trajectories of certain dynamic control systems. And that's a profound realization. It's a profound viewpoint. But of course, later the stochastics have to come back. And that's the subject of this third part of the talk, which is, so what if we're facing a real-world network where we don't have deterministic fluids flowing through it? Indeed, there are many levels of stochastic dynamics. For example, session level. Users, logical users, arrive with finite workload. They don't stay there forever with a static population. They're done the job, they leave. Packet level. Packets arrive in the same session in bursts, and they suffer probabilistic events individually along the way. Channel fluctuates, topology may even vary. For each of these levels of the stochastic dynamics, we would like to understand many things. For example, is still the deterministic formulation valid in the sense of giving the right engineering intuition? If we do that, can the queues remain stable? What about the probability distribution on performance like delay? Maybe you don't know the distribution, but you may know some statistics like the average, the outage. What would happen to fairness if you have like short flows coexisting with long flows with a different lifetime and so on? it turns out that this big table has many blank spots. Some more arbitrary grading scale I give. 3-star would mean completely done. Don't even try to work on that anymore. Blank is sort of nobody has a really conclusive starting point. 2-star, there are a couple of bright spots. So let me zoom into one bright spot and then ignore the rest of the table today. So this is the bright spot of session level stability. What does that mean? So look at the utility function, utility maximization problem. And now there's a dynamic user population with arrivals and departures. So S denotes the class of the users. N denotes at time t what is the number of active flows or active sessions in that class. And phi is the resource that belongs to a certain constraint set. It could be a time-invariant polytope, for example. It could be a time-varying non-convex set. It could be something simple to something very horrible. And you can do processor sharing among the flows that belong to the same class. And this is the problem you're trying to solve per time instant t. So departure clearly are governed by the service, which depends out of this constraint maximization problem. Arrivals assumed to be independent of the network state. Suppose they are Poisson arrival with exponential file size distribution, which is not true, but what is true, it turns out to be not tractable. So we have to say things that we can say in the paper. So let's say exponential distribution. All right, then we've got a Markov chain. Okay, the state evolves like this. It goes up with this rate. It goes down with this rate. Okay. Now the question is, what is the distribution of the buffer occupancy? Turns out that's too difficult a problem. Forget about that. Just ask about stability. For example, queue or rate stability, depending on which one you pick, of this queuing network. And this is a Markovian input, but a state-dependent service rate queuing network. The service rate is state-dependent precisely through the solution of this optimization problem, which in turn depends on the state of the queues and here. So there is a coupling between the deterministic optimization at each time and the evolution of the queuing dynamics. Okay. Well, the answer is the queues would be stable if and only if something. Right? Well, we know the necessary condition that the average intensity of the arrival must be within the constraint set of the deterministic optimization. So the real question is that also a sufficient condition for the queue stability of this queuing network? And the answer is yes, in many, 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 many cases. So this is a snapshot. It's not a comprehensive list of the papers that says the answer is yes for the case of this kind of arrival, this kind of topology, the utilities being the same across users or not, and the shape of the utility functions. Okay. However, the general question, general arrival, meaning doesn't have to be Poisson with exponential file size, general topology, possibly all kinds of concave utility function. What is the sufficient condition for stability? That is open. Here's something else that is recently solved by a group and collaborators. So instead of looking at the arrivals being more general, we look at the constraint set being more general. So the standard thing is time invariant convex. But in many cases, especially in wireless, you have a non-convex rate region. Okay? For example, you are doing random access-based allocation. You can have time variation of the rate region. So the question is, in this case, people have proved under those benign, mild arrival cases that the stability region of the deterministic num solution approach of resource allocation coincides with the rate region or the constraint set of the deterministic problem. Okay. Furthermore, that is the largest possible stability region you can ever get by whatever resource allocation. So it's the maximum stability region. Furthermore, well, obviously, it doesn't depend on the curvature of your utility shape. So none of those three statements are true, it turns out, if you have a non-convex or time-varying rate region. that the resulting stability region may be smaller than the actual rate region of the deterministic problem, that it depends on the curvature of the utility function, and that it is not necessarily the maximum stability region anymore. Okay. In fact, there may be an even trade-off between how fair you are, if you believe bigger alpha is more fair, versus how large your stability region is. There may be a strict trade-off there. So just want to illustrate that even in this one corner of this gigantic table on stochastic utility maximization, there are either surprises or big open problems not solved. Okay. Let me skip those couple of slides and then move on to, this is the last part, where I want to talk about another major challenge that we face, and it's a big challenge. I talked about the challenge of decoupling, and you have to do case-by-case hard work. Talked about the challenge of stochastics back into this deterministic fluid model, and there are many work that remains to be done in order for the theory to have a direct impact on the real dynamic network. And this is on non-convexity of your optimization model. And I'm sure most of you know very well that the watershed between easy and hard optimization problem, quoting Rockefeller, is not linearity but convexity. So what happens if it is a non-convex problem? I hate to invent more acronyms. This stands for Design for Optimizability, but it's such a cool one that hard to resist putting it there. What does that mean here? So let's again take a step back and look at what kind of non-convex problems you're going to encounter. They rise up in all kinds of corners for different reasons. Like you can have real-time application that gives you a sigmoidal utility function. You can have power control in low SNR, or many cases where the constraint set is non-convex. You can have integer constraints, or you can have a convex constraint, but it's going to take exponentially long description length to describe it. So that's still very hard, like certain scheduling problem where the number of activation sets is exponential in the number of nodes. So whenever these happens, and you know you are in a big trouble. So now what can you do? Mathematically, one thing that's good is that convexity, unlike, say, uniqueness of KKT points, is not an invariant quantity. So you can do a nonlinear change of variable, for example, like log change of variable in geometric programming, or embedding in the higher dimension, like sum of squares method, that gives you the convex geometry, even though it started out as being non-convex. But I'm not going to talk about that today. Instead, I'll advocate a more engineering approach. A fancy name is called Design for Optimizability. A more straightforward name is that ask your neighbor to change his assumption or to change his design so that you work on different assumption. And I'll illustrate that in an example of internet traffic engineering. But I still want to give you some pictures about perspectives. Okay, you say if this is non-convex optimization problem, and there are three broad approaches of attacking this problem. One is what I call go around non-convexity. Like you change a variable, you find conditions under which it is convex, or under which KKT point is unique, and so on. Second is to be brave and just sail through it. And things like sum of squares, signomial programming, in general, some kind of successive convex approximation to solve the problem. Or branch and bound, maybe in a very smart way, or use structures like difference of convex and generalized quasi-concavity and so on. But here's the third way, what I call going above non-convexity. So it comes out and goes back in there. That says, don't solve difficult optimization problem. Try to redraw the architectural protocol to make the problem easy to solve. Of course, you may have to pay a price for that, and that's the trade-off you have to be aware of. So in this case, optimization is not being used as a computational tool, not even used as a modeling language or an architectural understanding. It's actually used as a flag to say that certain design issues may be flawed. Because if you can help it, you shouldn't be tackling a difficult problem. Like if you're an instructor, you have the instructor of a course and the student at the same time, you shouldn't give yourself a hard midterm. So let me illustrate this with the last case, which is on internet traffic engineering within an autonomous system. So unlike what some people have the impression, like myself, before collaborating with people working on this subject, I thought, oh, how bad could that be, shortest path routing? It turns out it's really not shortest path routing. It's sort of the reverse of that. So the operator, say AT&T, would every now and then update a number per link called the link weight. And then from the control plane to data plane, give this link weight to the routers. And the routers would use link weights to construct the forwarding path. And then when the packet comes, look at the header, the destination address, and then forward the packet. So this is what they call link weight-based, hop-by-hop, destination-based packet forwarding. Okay, so some long phrase. And they want to do this so as to load balance the traffic in the procedure called traffic engineering. So there's a centralized computation to set the link weights. There's a distributed usage of the link weights to do packet forwarding based on destination only. Okay. OSPF is a major class, a major member of the class of such routing protocols. But people know that if you want to do best traffic engineering, OSPF will have to require exponential complexity. What is the best traffic engineering? So an operator assigns a metric like the cost of a link, which is a function of the utilization percentage. And usually that's modeled as after some queuing delay formula. And you want to minimize the sum across all the links. Or you want to minimize the maximum utilized links appearance. Or you want to delay the appearance of the congested link to as late as possible. So whatever metric you pick, there's a certain objective function there. But the variables are the link weights. So this is weird, right? The knobs are the link weights which you tweak. Tweaking the knobs would force the routers to allocate traffic in a different way by forwarding packets in different ways, which results in distribution of traffic different way, which changes your objective function's value. But the link weights do not directly change the objective function. So your monitor is here, your knob is there, and you have to indirectly influence that. And that's kind of weird, but that is how internet intra-AS routing is being done today. So we wonder, how can this problem of OSPF not being able to give you best traffic engineering in an efficient way? Don't even try to read this. This is a long list of a partial, actually very partial, list of outstanding work that's been done on the subject. The influential paper was in 2000 by Force and Thorup. Showed that it's NP hard to do best traffic engineering by OSPF, and you have to resort to local search methods, which is, set this industry standard for many years. Around the same time, actually before that, people started looking at something called MPRS, which enables you, as a forwarding mechanism, to do multi-commodity flow routing, which is what mathematically nicer, tractable, convex optimization solution. So that is good, but MPRS forwarding requires end-to-end tunneling, and that requires keeping a spatial memory. And that is not the philosophy of hop-by-hop destination-only forwarding. That may be one of the reasons why still people in the industry actually running the network love OSPF more than MPRS. So now the question is, can we get MPRS-like performance without MPRS complexity, without end-to-end tunneling? You still do local hop-by-hop forwarding of packets and yet be able to get to optimal traffic engineering. Is that possible or not? And we recently showed that it is possible. In fact, it's Infocom 08. There's an 07 paper that's been superseded by the 08 paper. And the idea of the protocol is extremely simple. The idea of the proof actually is quite interesting. So the protocol says the following. All right, you're going to use link weights to compute the path and decide traffic splitting pattern. But unlike OSPF, do not only construct shortest path and evenly split the traffic among the shortest path, but instead use all the path but put exponential penalty on longer path. Why exponential penalty? I'll come back to that in a minute. Now, this doesn't change any way you do the destination-based packet forwarding. However, it does change how does AT&T or any operator does the central computation of the link weights, because the link weights are now being used differently by the routers. That would mean it has to be computed in a different way by the operator. So the question is, could this new protocol be really good? And if so, how can the computation of link weights be done? Let's answer the first question first. One way to measure if this routing protocol is good or not is to compare with the benchmark of optimal traffic engineering, say, achieved by solving multi-commodity flow problem realized by, say, MPLS kind of forwarding. And y-axis is normalized to 1. What is that? It means that you increase the traffic load until at some point, for a given routing protocol, there will be a congested link, and you cannot increase everybody further. Stop, and then calculate the link utilization. For optimal traffic engineering, set that as the benchmark 1. Okay. Now you run a different routing protocol, presumably not as good. Then by the time you stop, the link utilization will be lower. And indeed, if you run OSPF, you're going to suffer some hit, sometimes big, sometimes small, for different kind of network. This is abelian network with certain traffic matrix recorded on a certain day and year. These are pretty standard artificially generated network topologies that this community often uses. But if you run what we call DEFT, or a sister version called PEFT, whatever they stand for, essentially this exponential penalty idea, then numerically you see it's almost always 1. In fact, we now can prove that it is 1, that it will achieve optimal traffic engineering exactly. Another way to measure it is to look at the optimality gap, which is the sum of the cost function, usually modeled after the MM1 queuing delay, over all the links inside the network. So these pictures look more impressive because DEFT is almost 0, and then OSPF shoots through a very high value. But this really is more of the artifact of the MM1 delay-based penalty function more than anything else. So if we want to get funding from certain agency, we would like to show this picture first. And show, you see, the network will explode if you don't do it our way. But really, this is a more meaningful one, which means, say, in an abelian topology, it gives you about 15% improvement just by being smarter on how you use the link weights. Okay? So the theorem is that link-based routing, link state routing with hop-by-hop destination-based forwarding can achieve optimal traffic engineering. And furthermore, the associated optimal weights computed by the operator can be done in polynomial time. In practice, it turns out that it's 2,000 times faster than the existing local search algorithms for OSPF link weights. So that means not only is better, it's also provably better. Not only it is faster, in theory, it's much faster in practice compared to local search heuristics of OSPF. How was the proof done? One picture to summarize that. Look at this is the set of all feasible flow routes. Okay, one point is one flow routing vector. And a subset of that is optimal with respect to your traffic engineering objective. But not all the members in this subset can be realized by link state routing with hop-by-hop forwarding. So our job is to pick out those that are not only optimal with respect to the objective function of your traffic engineering, but also realizable with link state routing. So how can I pick out those configurations? It turns out that we can construct another optimization problem purely as a proof technique for whatever constraint set, where the objective function is an entropy function. It's the entropy of a probability vector that describes the probability of going from your one node in the network to the final destination through different paths. Okay, and they normalize with total traffic intensity. You get a probability vector. Look at a certain normalized entropy function of that. Optimizing that, maximizing that normalized entropy function over possible configurations subject to a certain constraint set turns out will give you the elements in this subset. And the resulting cancellation of the terms is what leads to this exponential penalty. So the exponential penalty is direct consequence of this proof technique here. And it turns out we can also prove the other way around, that the entropy function is the only function subject to scaling, shifting, that can give you this picking ability. And exponential penalty is the only penalty. You can try others, any monotonic function. They would not be able to give you proof of optimal traffic engineering. So the details, again, are in papers that you can download. If you remember the DSL story, we talk about the coupling side. There's another side, which is the non-convexity side. It turns out that somehow it performs very well, right? You probably should have asked a question, at least in your own mind at that point, which is, all right, I can see the decoupling using static pricing, but how come that the achieved rate region is so close to optimal? Isn't that a non-convex problem? It turns out that somehow the hard problems in that instance aren't hard in reality. By reality, I mean what? I mean that you can give me a DSL spectrum management problem as a mathematical problem, and then you can give me some description of the constant parameter of the cross-channel coefficients, such that any suboptimal heuristic can work very poorly. Okay, that's mathematically doable. But these crosstalk coefficients are not mathematical constructs. They are representation of the physical reality of the law of electromagnetic radiations. So somehow, in this tough landscape of non-convex problem, so imagine given non-convex problem, you've got a landscape with local maxima, global maxima, and then local, global minimum, so on. The instances that are physically meaningful, those parameters will lead to a terrain of this problem where the location, number, and value of the local maxima are not that bad compared to the global maxima. As to why that is the case, can we prove a statement such that, for a certain subset of these cross-gain coefficients, not only can we prove convergence, which we have done, but we can also prove optimality altogether? We wish we'll be able to do that. We are not yet. And this routing story just shows that sometimes hard problems don't deserve to exist altogether. In this case, it's not coupling of electromagnetic radiation that's bothering you. It's this assumption that you have to pick only shortest path and equally split traffic among them. Given the link weights, there's no reason why you have to use link weights in that particular manner. So that engineering assumption actually does not match optimal traffic engineering. No wonder it didn't work in a polynomial time before. So instead of going on from a restrictive assumption to some intractable formulation, forget about the past, try to be brave with non-scalable solution, maybe we should just take a minute to say, the fact that this optimization coming out of an engineering assumption becomes intractable is a signal, a flag that tells me maybe the assumptions can be perturbed. For example, in this case, relax to allowing whatever monotonic penalty function, turns out exponential penalty function works great, such that I end up with a tractable formulation and then scalable solution. So this is what we call a feedback, not in the network, but in the human thinking procedure, in the engineering process. This feedback is very important. So next time, maybe looking at a hard problem, that should be alerting you to knock on the door of your neighbor. Say, 10 years ago, you did something, you made a decision for no good reason, or for some good reason, but now there are other reasons that may supersede that reason. And maybe we can talk about changing your decision now. Okay, so most likely you have to pay a price for revisiting the assumptions because they are often made with good engineering intuitions, not for zero reason. In this case, it turns out you're not really paying much price at all. You can provably get optimality, and it remains as simple as OSPF. You have to do more computation at the operator and at the router, but those computations are cheap. The key thing is you don't need tunneling, you don't need spatial memory. a little price you have to pay is an out-of-order package arrival, although that can also be dealt with in different ways. So I'm going to skip this complexity part. It turns out there's some interesting story recently been developing on scheduling where we look at the trade-off between complexity and optimality in a three-dimensional system. But let me conclude this talk here. Back to the first slide where I said that when you look at optimization of network, if you can, please do not just think about that as a computational tool to help you solve a minimization, maximization problem, even though that is still a useful thing to have, and sometimes it does happen as well. But think of that more as a way to do modeling, whether it's forward or reverse engineering, as a way to quantify mathematically architectural decisions and statements, as a way to connect to robustness, as a way of giving feedback to your engineering assumptions. So if you take away optimality, then what do you have left with optimization? I think you have something that's much more open-minded and much more powerful. Optimization for networking as a language to think about choices and decisions in network engineering. That I'll conclude. Thanks for your attention. Questions? Yuna?
About that.
Yes.
So you mentioned that you challenged the assumption that the conventional assumption where you do shortest path routing and equal splitting among the shortest passes. And intuitively, this is good. You want to find shortest paths. What's wrong with this?
Yeah. So because it is not matching the definition of optimal traffic engineering, which is to minimize, I didn't show you, I perhaps should have, minimize the sum of the cost function over all the links. The objective is not to compute the shortest path, is to minimize the total congestion cost function across the entire network. So really what you want to do is load balancing. Shortest path is a very nice load balancing, but will that be able to give you optimal load balancing? People had hope before 2000. Then Force and Thorpe paper showed that not really, unless you are willing to have exponential complexity of computing the link weights. So polynomial time complexity of computing the link weights such that the resulting link weights, if used only to do shortest path routing, cannot give you a load balancing that is 100% perfect with respect to a congestion cost function. And that's what they did in 2000. So then people went to the other extreme and start feeling that it's hopeless, it's impossible to have. The answer is OSPF cannot give you that. That doesn't mean that any other link state routing protocol cannot give you that either. So in fact, there were paper, for example, I just cited paper in 2005 that inspired our work that shows, well, what if you try other penalty functions? Not just Boolean penalty, because shortest path is a Boolean penalty, right? If you are on the you are a shortest path, or you are not. If you are, count how many you are, divide by that number. That's the traffic splitting. If you are not, you get 0 loaded on you. Then people have started thinking about maybe I do a penalty function 1 over the sum of the path cost, link path weight, or maybe exponential penalty, or maybe other function. And what we did is to show that based on those ideas, we can refine the ideas to the degree that is actually provable, that one of these alternative penalty functions can give you exactly the optimal traffic engineering. So to answer your question in short, because load balancing in the meaning of optimal traffic engineering is not equivalent to shortest path. Yes?
So the global objective function you're talking about is the sum of the delay on, or like the congestion on edges, or the maximum?
Right. So it turns out that it can be any convex function composed. So each link, you look at the convex function of the link utilization percentage. For example, piecewise linear approximation of the MM1 delay as a function of the utilization. And then look at across all the links, you can pick any convex function. Sum is one, max is another, of those convex function. composed with those functions, and that is the cost function.
With these exponential penalty functions, you can optimize any
of these convex, as long as it's a convex function composing with individual convex functions. In practice, what operator use is the sum of the convex cost functions.
What is this, like, what do you mean by this exponential penalty function? So let's say you know like the weight of the path.
Right, so I've got two paths, one path's path weight is 10, the other path weight is 20. Then this is e to the minus 10 divided by e to the minus 10 plus e to the minus 20. And the other is e to the minus 20 divided by e to the minus 10 plus e to the minus 20.
But if you want to do next hop, I mean, if you can choose, if it's MPLS, you can choose the path, you can choose what fraction to send on each path.
Yeah.
But if you want to do next hop, you have to aggregate this for next hop.
Right. So it turns out that you can do a local decision only looking to the destination without looking back to the source. And then you can make this local decision about path splitting in the depth or path scheme that we proposed. And that is one tweak that I didn't go into the detail. But indeed, if you need end-to-end enumeration of all the paths, that would have been just like MPRS. No, you don't need to do that. You only need to, from you forward to destination. In fact, you don't even need to enumerate all the possible paths. There's a recursive computation in our paper that does that.
So you can simulate this, like all these different paths by...
Essentially, yes. That you can simulate the solution to this, what we call network entropy maximization, that lead to all these cancellation of the terms based on a recursive counting of the alternative path, looking only forward to the destination without spatial memory. Yes?
So I have a question. So I'm thinking, so this this work of computing OSPF weights to do traffic engineering, that started Mikkel, Thora, Petiti, and T, and it seems where they were coming from, they were having so many legacy routers, and MPLS was a relatively new technology.
Yes.
So they wanted, kind of retrofit OSPF weight fudging to do MPLS kind of traffic engineering. But what I'm trying to understand here, MPLS buys you a lot of flexibility. You can do traffic engineering per class of traffic. You can do things like oblivious routing when your traffic is variable. So is this like, is there an easy answer to say I can do away with MPLS because I can solve a certain class of problems using OSPF forwarding?
Sure. Yeah. So two things. First, my understanding is, which I could be totally wrong, is that MPLS in the 90s invented a lot of excitement, but then people start feeling that maybe end-to-end memory is just not the right way to go forward with legacy. And Foss and Thorpe show that, but OSPF can't do it exactly right, but here are local search method that gets it very well. Now, second, does this mean, therefore, that with deft and peft, MPLS will never be useful again? No, because deft and peft can provably get to the optimal traffic engineering with respect to that objective function. Now, if your objective function changes, for example, to the idea or to the notion of being flexible, however that might be mathematically represented or not, right? Then clearly you're dealing with a different optimization problem. And the flexibility, whether it's oblivious routing or QoS routing with guarantee of delay and so on and so forth, MPLS being an end-to-end tunneling mechanism gives you a lot more power, a lot more freedom. Some of these power may not be captured by any link state routing protocol, including PathDeft or OSPF. So indeed, if you say, I don't care just about optimal traffic engineering, I care about many, many other things as well, they're also my objective function, then there's been no study, because of the very reason, whether DefPath can do that, and I suspect they cannot do them all, because they are relying on a very simple description. Each link has one number, and a very simple decision rule, only destination-based hop-by-hop forwarding. I really doubt if with such limited gunpower, you can kill all these beasts, oblivious routing, QoS routing. I have big doubt about that. but nobody has looked at that. But the answer is, indeed, MPLS still has its merits. And whether it will be widely used or not will depend on factors outside technology.
Any other questions?
Okay, thank you.